Hello, and welcome. I'm so glad you found your way here tonight, to this quiet space where science and stillness meet. You may be tired. Perhaps your mind has been moving quickly all day, spinning through tasks and thoughts and the bright noise of the world. That's perfectly all right. You don't need to do anything now except rest. Let your shoulders soften. Let your breathing slow. You can close your eyes if you wish, or simply let them rest gently on a point in the distance, unfocused and calm. Tonight, we're going to explore something truly soothing, something that happens far beyond the rush of daily life, out in the vast and patient darkness of space. We're going to talk about light, how it travels, how it fades, how it is gently absorbed by the cosmos itself. There is something deeply peaceful about understanding how photons, those tiny messengers of energy, drift through the universe, sometimes for billions of years, only to be quietly caught, transformed, and stilled. It's a story without urgency, a process that unfolds across distances so immense that time itself seems to slow down. If you'd like to return to this kind of calm exploration again, you're welcome to follow along for more gentle science stories. But there's no pressure at all. You're here now, and that's enough. So let's begin, softly and slowly, with the nature of light itself. Light is not a thing you can hold. It is real. It moves through space as both a wave and a particle, a duality that scientists have come to accept with a kind of quiet wonder. When we speak of light being absorbed, we mean that its energy is taken in by something else, an atom, a molecule, a grain of dust, a cloud of gas. The photon, that particle of light, gives up its energy and ceases to exist as light. It becomes heat, or it nudges an electron into a higher state, or it contributes to a chemical change. This transformation is gentle, invisible, and happens everywhere, all the time, throughout the universe. In the emptiness of space, light can travel for extraordinary distances without being absorbed at all. The vacuum between stars is so sparse, so nearly perfect in its emptiness, that a photon can journey for millions of years and never encounter a single atom. This is why we can see galaxies that are billions of light years away. Their light has traveled across the universe, patient and undisturbed, until it finally reaches our eyes or our telescopes. It's a kind of cosmic endurance, a slow and steady crossing of the dark. But space is not completely empty. There are thin veils of gas, clouds of dust, and the occasional wandering molecule. When light meets these scattered bits of matter, something quiet happens. Some photons pass through unaffected. Others are absorbed. The ones that are absorbed transfer their energy to the atoms they encounter, and in doing so, they disappear. The atom might warm ever so slightly, or an electron might jump to a higher orbit, holding that energy for a moment before releasing it again, often as a photon of a different color, a different energy. This process of absorption and re-emission is one of the most fundamental interactions in the universe. It is how stars warm planets. It is how nebulae glow. It is how the early universe, once opaque and blazing, gradually became transparent as matter cooled and spread apart. Every time you see a color in the sky, whether it's the blue of Earth's atmosphere or the red of a distant nebula, you are witnessing the results of countless tiny absorptions and releases, a conversation between light and matter that has been going on since the beginning of time. Let's consider the color of light for a moment. Light comes in many wavelengths, from the long, lazy waves of radio to the short, energetic pulses of gamma rays. Visible light, the kind our eyes can see, sits in the middle of this spectrum, a narrow band of wavelengths that we experience as colors. Red light has a longer wavelength, blue light a shorter one. When light is absorbed, the wavelength matters. Different atoms and molecules absorb different colors. Hydrogen, for instance, absorbs very specific wavelengths, creating dark lines in the spectrum of a star. These lines are like fingerprints, telling us what elements are present, even across vast distances. In space, dust plays a surprisingly important role in absorbing light. These grains are unimaginably small, often just a fraction of a micron across, made of carbon, silicates, and sometimes ice. When starlight passes through a cloud of dust, the shorter wavelengths, the blues and violets, are more likely to be scattered or absorbed. The longer wavelengths, the reds and oranges, pass through more easily. This is why distant stars sometimes appear redder than they truly are. The dust between us and them has gently filtered the light, absorbing the blue and letting the red continue on its way. Astronomers call this interstellar reddening, and it's a quiet reminder that space, though vast, is not entirely transparent. The absorption of light by dust is not violent or dramatic. It is a slow, cumulative process. A single grain of dust might absorb only a few photons over the course of years. But when you have trillions upon trillions of grains spread across light years of space, the effect becomes significant. Entire regions of the galaxy can be dimmed or hidden from view, cloaked behind veils of absorbing dust. These are the dark nebulae, the shadowy patches you can see in photographs of the Milky Way, where fewer stars shine through. They are not empty. They are full of dust and gas, quietly absorbing the light from the stars beyond. One of the most beautiful examples of light absorption in space is found in the planetary nebulae. These are the glowing shells of gas that some stars shed at the end of their lives. The central star, now a hot white dwarf, emits intense ultraviolet light. This light is absorbed by the surrounding gas, which then re-emits it as visible light in specific colors, often green from oxygen, red from hydrogen, blue from helium. The nebula glows not because it is hot in the way a fire is hot, but because it is absorbing and transforming the energy of the star at its heart. It is a gentle alchemy, light changing form, energy passing from one state to another. In the vast spaces between galaxies, there is an even thinner medium, a whisper of hydrogen and helium left over from the Big Bang. This intergalactic medium is so diffuse that you could travel through it for years and never notice it. Yet even here, light can be absorbed. When light from a distant quasar passes through this medium, the hydrogen atoms along the way absorb specific wavelengths, creating what astronomers call the Lyman alpha forest, a series of dark lines in the quasar spectrum, each one marking a cloud of hydrogen somewhere along the line of sight. It is a map written in absorbed light, tracing the invisible structure of the universe. The absorption of light is also how we know the universe is expanding. When a galaxy moves away from us, its light is stretched, shifted toward the red end of the spectrum. This redshift is not caused by absorption, but the two phenomena are related. As light travels through expanding space, it loses energy, its wavelength lengthens, and it becomes redder. In a sense, the universe itself is gently absorbing energy from the light that crosses it, though not in the way matter does. The photons remain, but they carry less energy with each passing in. It is a kind of cosmic weariness, a slow dimming that happens over billions of years. Black holes, those mysterious regions where gravity is so strong that nothing can escape, also absorb light in their own way. Any photon that crosses the event horizon is lost forever, pulled into a place from which no information can return. But even before reaching that point of no return, light can be absorbed by the swirling disk of matter that often surrounds a black hole. This accretion disk is incredibly hot, and as matter spirals inward, it emits light across the spectrum. Some of that light is absorbed by the disk itself, heating it further, creating a feedback loop of energy. The light we see from these systems is what manages to escape, a fraction of the total energy being released. Let's turn our attention now to the sun, our own star, and consider how light is absorbed even within it. The sun's core is a furnace of nuclear fusion, where hydrogen atoms are crushed together to form helium, releasing enormous amounts of energy in the process. This energy is born as gamma rays, the most energetic form of light. But the sun is not transparent. It is dense with matter, and those gamma rays cannot simply stream outward. Instead, they are absorbed almost immediately by the surrounding plasma. An atom absorbs a photon, heats up, and then re-emits another photon, often at a slightly lower energy. This new photon travels a tiny distance before it, too, is absorbed and re-emitted. This process happens over and over again, billions upon billions of times. A single packet of energy, born in the core, takes thousands of years to work its way to the surface, bouncing from atom to atom in a random walk that is both patient and persistent. By the time the energy finally reaches the sun's surface and escapes into space, it has been transformed. What began as a gamma ray has become visible light, the warm yellow glow that reaches Earth and makes life possible. The absorption and re-emission of light within the sun is a kind of cosmic digestion, a slow transformation of energy from one form to another. When sunlight finally leaves the sun and travels through space, it takes just over 8 minutes to reach Earth. Most of it arrives unimpeded, crossing the vacuum without encountering anything that might absorb it. But when it reaches our atmosphere, the process of absorption begins again. The molecules of nitrogen and oxygen in the air absorb and scatter the sunlight, particularly the shorter blue wavelengths. This is why the sky appears blue during the day. The blue light is scattered in all directions, filling the sky with color, while the longer red wavelengths pass more directly through. At sunrise and sunset, when the light must travel through more of the atmosphere, even more blue is scattered away, and the sky takes on those soft hues of orange and pink. The Earth's atmosphere also absorbs certain wavelengths of light very effectively. Water vapor, carbon dioxide, and ozone all absorb infrared light, the kind of light that carries heat. This absorption is what makes our planet warm enough for life. Without it, the Earth would be a frozen, lifeless rock. The greenhouse effect, as it's called, is a delicate balance of absorption and re-emission. The surface of the Earth absorbs sunlight and warms up, then radiates that heat as infrared light. Some of that infrared escapes to space, but much of it is absorbed by greenhouse gases in the atmosphere, which then re-radiate in all directions, including back toward the ground. It's a gentle blanket of energy, of absorption that keeps us warm. Plants, too, are masters of light absorption. The green leaves of trees and grasses contain chlorophyll, a molecule that absorbs red and blue light very efficiently, while reflecting green. This is why plants appear green to our eyes. The absorbed light provides the energy for photosynthesis, the process by which plants convert carbon dioxide and water into sugar and oxygen. It is one of the most important chemical reactions on Earth, and it is powered entirely by the absorption of sunlight. Every breath you take, every bit of food you eat, traces back to this quiet process of light being captured and transformed by the living world. In the ocean, light absorption follows a different pattern. Water absorbs red light very quickly, within just a few meters of the surface. As you descend deeper, the world becomes bluer and dimmer, because blue light penetrates farther than any other color. Below about 200 meters, there is no sunlight at all, only darkness. Yet even in this deep darkness, there is light, bioluminescence, created by living creatures. These organisms produce light through chemical reactions, and that light, too, can be absorbed by the surrounding water or by other creatures. It is a hidden world of glowing and fading, of light being made and absorbed in the cold, quiet depths. Let's drift now to the edges of our solar system, where the sun's light grows faint. Out beyond Neptune, in the realm of the Kuiper Belt, sunlight is weak and cold. The objects here, icy bodies, dwarf planets, ancient remnants of the solar system's formation, still absorb sunlight, but the effect is subtle. Their surface is warm only slightly, and any ice that absorbs enough energy might slowly sublimate, turning directly from solid to gas. This is how comets form their tails when they swing close to the sun. The ice absorbs sunlight, vaporizes, and the gas and dust are blown outward by the solar wind and radiation pressure. It is a slow unveiling, a gradual transformation driven by the patient absorption of light. Comets themselves are beautiful examples of light absorption and scattering. As a comet approaches the sun, its nucleus, a dirty snowball of ice and rock, begins to warm. The ice absorbs sunlight and sublimates, releasing gas and dust into space. This material forms a glowing cloud around the nucleus, called the coma, and a long tail that can stretch for millions of kilometers. The coma glows because the gas molecules absorb ultraviolet light from the sun and re-emit it as visible light, a process called fluorescence. The dust in the tail scatters sunlight, reflecting it toward Earth, which is why we can see the tail, even though it is incredibly thin, far more tenuous than any vacuum we can create on Earth. There are places in space where light is absorbed so thoroughly that almost nothing escapes. These are the dense cores of giant molecular clouds, the birthplaces of stars. Within these clouds, the dust is so thick that visible light cannot penetrate. If you were somehow inside one of these clouds, you would be surrounded by utter darkness, even though stars might be forming all around you. The only light that can pass through is infrared, with its longer wavelengths. This is why astronomers use infrared telescopes to study star formation. The infrared light is absorbed less by the dust, allowing us to peer into these hidden nurseries and watch as gravity pulls matter together, as protostars ignite, as planetary systems begin to take shape. The absorption of light in these clouds also plays a role in cooling the gas. When a molecule absorbs a photon, it can become excited, and then it may release that energy by emitting a photon of a different wavelength, often in the infrared. This emitted light can escape the cloud, carrying energy away and allowing the gas to cool. Cooler gas can collapse more easily under its own gravity, so the absorption and re-emission of light is part of the process that allows stars to form. It is a feedback loop, a conversation between light and matter that shapes the structure of galaxies. In the early universe, just a few 100,000 years after the Big Bang, the cosmos was filled with a hot, dense plasma of electrons and protons. Light cannot travel freely through this plasma. Photons would be absorbed and scattered almost immediately, making the universe opaque, like a thick fog. But as the universe expanded and cooled, the electrons and protons combined to form neutral hydrogen atoms. This process, called recombination, changed everything. Neutral hydrogen does not interact with light as strongly as free electrons do. Suddenly, the universe became transparent. Light could travel freely for the first time. The photons that were released at that moment have been traveling ever since, and we see them today as the cosmic microwave background, a faint glow that fills the entire sky, the oldest light in the universe. This ancient light has been absorbed and redshifted by the expansion of the universe. What was once visible and even ultraviolet light is now microwave radiation, with wavelengths measured in millimeters. It has cooled to just a few degrees above absolute zero, yet it still carries information about the early universe, about the tiny fluctuations in density that would eventually grow into galaxies and stars. By studying how this light has been absorbed and scattered over billions of years, astronomers can map the history of the cosmos. tracing the evolution of structure from the smooth, hot beginning to the rich, complex universe we see today. There are also regions of space where light is absorbed by ionized gas, creating what are called HI regions. These are clouds of hydrogen that have been ionized by the intense ultraviolet light from young, hot stars. The hydrogen atoms absorb the UV photons, which strips away their electrons. The free electrons eventually recombine with protons, and when they do, they emit light at specific wavelengths, particularly the red glow of hydrogen alpha. These regions are among the most visually stunning objects in the night sky. Bright, colorful nebulae like the Orion Nebula or the Eagle Nebula. They are places where light is being absorbed and transformed on a grand scale, where the energy of starlight is reshaping the surrounding gas, sculpting it into pillars and waves and glowing arcs. The absorption of light is not always a one-way process. Sometimes, light can stimulate an atom or molecule in such a way that it emits more light than it absorbed. This is the principle behind lasers, though natural lasers, called masers, also exist in space. In certain regions, such as around young stars or in the atmospheres of old, dying stars, molecules like water or hydroxyl can be pumped into excited states by absorbing light or colliding with other particles. When these molecules release their energy, they do so in a coordinated way, emitting microwaves that are coherent and intense. These cosmic masers are beacons in the radio spectrum, helping astronomers map the motions and structures of distant clouds and stellar environments. Let's consider now the role of light absorption in the life cycle of stars. A star like the Sun will shine steadily for billions of years, fusing hydrogen into helium, radiating light into space. But eventually, the hydrogen in the core runs out. The core contracts and heats up, and the outer layers expand, turning the star into a red giant. During this phase, the star's outer atmosphere becomes cool and distended, and molecules can form. Carbon monoxide, water, even complex organic compounds. These molecules absorb light from the star's core, and they also absorb and re-emit infrared radiation, creating a thick, dusty envelope around the star. This envelope absorbs much of the visible light, making the star appear dimmer and redder than it truly is. Eventually, the star will shed these outer layers entirely, creating a planetary nebula, and the cycle of absorption and emission will continue in a new form. More massive stars end their lives in supernova explosions, events so bright that they can briefly outshine an entire galaxy. In the moments after a supernova, light and matter are flung outward at tremendous speeds. The expanding shell of gas is incredibly hot and dense, and it absorbs and emits light across the entire spectrum. Over time, as the shell expands and cools, the absorption changes. Heavy elements created in the explosion, iron, nickel, cobalt, absorb specific wavelengths, creating a complex spectrum that astronomers can study to understand what happened deep inside the star. The light we see from a supernova is a record of absorption and emission, a story written in the language of photons and atoms. Neutron stars, the remnants left behind by some supernovae, are among the densest objects in the universe. Their surfaces are so hot that they emit X-rays, and the intense gravity bends and distorts the light in strange ways. But even neutron stars can absorb light. If a neutron star is in a binary system, pulling matter from a companion star, that matter forms an accretion disk. The disk absorbs X-rays from a neutron star and re-emits them, creating a complex pattern of absorption lines that can reveal the composition and motion of the infalling gas. It is a violent environment, yet the physics of light absorption remains the same. Photons are captured, energy is transferred, and new light is born. In the vast stretches between stars, there are also free-floating planets, rogue worlds that have been ejected from their solar systems, and now drift alone through the galaxy. These planets receive no light from a nearby star, yet they are not completely dark. They still retain heat from their formation, and they glow faintly in the infrared. If such a planet has an atmosphere, that atmosphere will absorb and re-emit the planet's own heat, creating a subtle greenhouse effect even in the absence of a sun. These lonely worlds are reminders that light absorption is not just about starlight. It is about any transfer of energy, any interaction between radiation and matter, no matter how faint or far from home. There are clouds in space called reflection nebulae, where light is not absorbed but scattered. These nebulae are made of dust that is too cool to emit its own light, but they lie near bright stars. The starlight scatters off the dust grains, reflecting toward us, and because shorter wavelengths scatter more efficiently, these nebulae often appear blue. The Pleiades star cluster is surrounded by such a nebula, a delicate blue haze that seems to cradle the young stars. It is a reminder that not all interactions between light and matter involve absorption. Sometimes, light simply changes direction, bouncing gently off the surfaces of tiny grains, continuing its journey in a new direction. Even the light from the most distant galaxies, those at the very edge of the observable universe, has been affected by absorption. As their light travels toward us, it passes through countless clouds of gas, each one absorbing a little bit of light at specific wavelengths. By studying these absorption lines, astronomers can map the distribution of matter throughout the universe, tracing the cosmic web of filaments and voids that defines the large-scale structure of space. It is like reading a history book written in light, each absorption line a chapter, each galaxy a word in the long story of the cosmos. There is something deeply calming about the fact that light absorption is such a gentle, universal process. It happens everywhere, all the time, without drama or haste. A photon travels for millions of years, and then, in an instant, it is absorbed, its energy transformed, its journey ended. And yet, in that ending, there is a beginning, a warmed atom, a shifted electron, a new photon born. The universe is constantly recycling light, transforming it, passing it from one form to another in an endless, patient dance. We continue now into deeper territory, where light meets matter in ways both subtle and profound, and where the universe reveals its quieter transformations. Let your breathing settle as we explore these gentle interactions, these soft collisions between energy and substance that shape everything we see and everything hidden beyond sight. Consider for a moment the journey of a photon through a molecular cloud, one of those vast regions where gas and dust gather in the space between stars. The photon enters this cloud, traveling at its constant, unwavering speed, and immediately the environment changes. Molecules of hydrogen, carbon monoxide, and more complex compounds float in the darkness, each one a potential obstacle, each one capable of absorbing specific wavelengths of light. The photon may pass through unhindered for light years, or it may strike a molecule within moments. When absorption occurs, the photon ceases to exist as light, and its energy becomes something else entirely. A vibration within the molecule, a rotation, a shift in electronic state. The molecule grows warmer by an infinitesimal amount, or it may re-emit the energy as a different wavelength, softer and redder than before. This is not destruction, but transformation, a gentle exchange that happens trillions upon trillions of times throughout the cosmos. And within these molecular clouds, certain molecules are particularly skilled at absorbing light. Water vapor, even in the frozen reaches of space, absorbs infrared wavelengths with remarkable efficiency. Carbon dioxide molecules resonate with specific infrared frequencies, capturing photons that match their internal vibrations. Complex organic molecules, some containing dozens of atoms, create intricate patterns of absorption across multiple wavelengths, like fingerprints that astronomers can read from vast distances. Each molecule tells a story through the light it takes in, through the specific energies it accepts and transforms. This selectivity means that white light entering a molecular cloud emerges changed, filtered, with certain colors stolen away and others allowed to pass. The cloud itself becomes a kind of cosmic prism, not separating light, but editing it, choosing which wavelengths will continue their journey and which will be absorbed into the slow dance of molecular motion. Moving outward from molecular clouds, we encounter the phenomenon of light absorption by free electrons, those unbound particles drifting through the ionized regions of space. When a photon passes near a free electron, something called Thomson scattering can occur. The photon bounces off the electron, changing direction but not energy, unless the photon carries tremendous energy, in which case Compton scattering takes over, and the photon loses some of its energy to the electron. These interactions are probabilistic, governed by quantum mechanics, and they create a kind of fog through which light must navigate. In regions where free electrons are abundant, such as the hot gas surrounding galaxy clusters, this scattering and partial absorption can significantly alter the light passing through. The cosmic microwave background itself, that ancient light we discussed earlier, shows tiny distortions called the Sunyaev-Zel'dovich effect, where photons gain energy by scattering off hot electrons in galaxy clusters. The cold photons arrive, interact with the energetic electrons, and leave slightly warmer, slightly bluer. It's a gentle heating, a transfer of energy from matter to light, the opposite of typical absorption, but equally revealing about the conditions in space. Let us drift now toward the surfaces of planets, where atmospheres create layered systems of absorption unlike anything in the vacuum of space. On Earth, our atmosphere absorbs ultraviolet light through ozone molecules in the stratosphere, protecting life below from harmful radiation. Each ozone molecule can absorb a UV photon, which breaks the molecule apart into oxygen molecules and free oxygen atoms. But these quickly recombine, reforming ozone and releasing the absorbed energy as heat. This cycle repeats continuously, creating a warm layer in the stratosphere where absorption is most intense. The process is so effective that very little UVC radiation, the most dangerous type, reaches the surface. This absorption is not merely protective, it's generative, creating temperature gradients that drive atmospheric circulation, shaping weather patterns, influencing the movement of air masses across the globe. Light absorption becomes a sculptor of climate, a quiet architect working through molecular interactions too small to see, but vast in their cumulative effect. Other planets show different absorption signatures. Venus, wrapped in thick clouds of sulfuric acid in an atmosphere rich in carbon dioxide, absorbs visible and infrared light with extraordinary efficiency. Sunlight that penetrates to the surface warms the ground, which then radiates infrared light upward. But this infrared cannot escape. The carbon dioxide molecules absorb it, vibrate with the added energy, and re-emit it in random directions, much of it back downward. This is the greenhouse effect in its most extreme form, a runaway process of absorption and re-emission that has heated Venus to temperatures exceeding 450 degrees Celsius. The light enters, transforms to heat, and becomes trapped in an endless cycle of absorption. It's a reminder that absorption is not always gentle in its consequences, though the mechanism itself remains the same. Photons meeting molecules, energy changing form, the universe following its fundamental rules without judgment or intent. On Mars, the thin atmosphere absorbs relatively little light, allowing most solar radiation to reach the rusty surface directly. But what little atmosphere exists, mostly carbon dioxide, still plays a role. Dust suspended in the Martian air absorbs and scatters light, creating the planet's characteristic salmon-colored sky. The dust particles are fine, rich in iron oxides, and they interact with blue light more than red, scattering the blue away and allowing red wavelengths to dominate the sky's appearance. When dust storms envelop the planet, absorption increases dramatically, reducing the sunlight reaching the surface and cooling the ground, which in turn affects atmospheric dynamics. Even on a world with barely 1% of Earth's atmospheric pressure, light absorption shapes the environment, drives change, and creates the conditions that define the planet's character. Turning our attention to the gas giants, we find absorption occurring in deep, layered atmospheres where pressure and temperature vary enormously with depth. Jupiter's atmosphere, composed mainly of hydrogen and helium with traces of methane, ammonia, and water, absorbs light in complex patterns. Methane absorbs red light strongly, which is why Jupiter's high-altitude hazes appear somewhat blue in detailed images. Ammonia clouds reflect white and tan colors, while deeper compounds, perhaps including complex organic molecules created by lightning and solar radiation, absorb across various wavelengths, creating the planet's bands of color. Each layer absorbs different wavelengths, and the light we see from Jupiter has been filtered through this atmospheric stack, with certain colors removed and others enhanced. The Great Red Spot, that enormous storm, appears red partly because of the compounds within it that absorb blue and green light, allowing only the longer wavelengths to reflect back to space. Absorption here is tied to chemistry, meteorology, and the slow churning of a planet-sized atmosphere. Let us consider now the absorption of light by ice, a substance abundant throughout the outer solar system and beyond. Water ice is highly reflective in visible light, which is why icy moons like Europa and Enceladus shine so brightly. But ice absorbs infrared light quite effectively, particularly at wavelengths around 3 micrometers. This absorption is due to the molecular vibrations of water molecules locked in the crystalline structure. The photons excite these vibrations, and the energy dissipates as subtle warmth within the ice. On airless bodies, this absorbed energy can slowly sublime ice directly into space, molecule by molecule, over millions of years. On bodies with thin atmospheres, like Pluto, the absorbed sunlight can drive seasonal cycles, warming nitrogen ice until it vaporizes, creating a temporary atmosphere that later refreezes when the dwarf planet moves farther from the sun. Ice absorption is a gentle process with long-term consequences, shaping surfaces and atmospheres across vast timescales. Comets offer another beautiful example of light absorption in action. As a comet approaches the sun, solar radiation begins to warm its surface, which is a mixture of ice and dark, carbon-rich dust. The ice absorbs infrared light and begins to sublime, releasing gas that carries dust particles with it. This creates the coma, the glowing cloud around the nucleus, and eventually the tail. The dust in the tail absorbs sunlight and also scatters it, creating the broad, curved dust tail visible from Earth. Meanwhile, the gas in the tail absorbs ultraviolet light, which ionizes the molecules and causes them to fluoresce, emitting their own light and creating the straight, blue ion tail. The comet becomes a laboratory of absorption and emission, a small body transformed by light into something magnificent and ephemeral. When the comet retreats to the outer solar system, the process reverses. The absorption decreases, the tails fade, and the nucleus returns to its frozen slumber. We can drift now beyond our solar system to consider how light absorption affects the detection of exoplanets, those worlds orbiting distant stars. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the star's light. This is the transit method, one of the most successful techniques for finding exoplanets. But the planet doesn't merely block light. Its atmosphere, if it has one, also absorbs specific wavelengths. By comparing the star's light during the transit with its light before and after, astronomers can detect these absorption features and identify molecules in the planet's atmosphere. If water vapor is present, it will absorb infrared light at characteristic wavelengths. Sodium absorbs yellow light. Methane, carbon dioxide, and even more exotic compounds each leave their signatures. The planet's atmosphere becomes a backlit screen, and absorption is the ink that writes its composition across the spectrum. This is how we've detected water on worlds dozens of light years away, how we've found clouds, hazes, and even hints of weather on planets we'll never visit. Absorption makes the invisible visible, translating distant chemistry into patterns of light we can read. Some exoplanets absorb light in extreme ways. Hot Jupiters, gas giants orbiting very close to their stars, have atmospheres heated to thousands of degrees. At these temperatures, molecules break apart into atoms, and even atoms can lose electrons, becoming ionized. The absorption spectrum of a hot Jupiter is dramatically different from a cooler planet. Instead of molecular bands, we see atomic lines, the signatures of iron, magnesium, and other elements in gaseous form. Some hot Jupiters are so hot that they absorb nearly all incoming light, reflecting almost nothing, making them darker than charcoal. These worlds are called hot because of their temperature, but they might better be called dark because of their absorption. Light arrives, is captured by the scorching atmosphere, and transforms entirely into heat, driving fierce winds that race around the planet at thousands of kilometers per hour. Absorption here is total, relentless, and it creates some of the most extreme environments imaginable. Let us turn our gaze to the absorption of light by rocky surfaces, the solid crusts of planets, moons, and asteroids. Different minerals absorb different wavelengths based on their chemical composition and crystal structure. Iron-rich minerals tend to absorb blue and green light, reflecting red and making surfaces appear rust-colored, like Mars. Minerals containing water or hydroxyl groups absorb specific infrared wavelengths, revealing the presence of hydration even from orbit. Olivine, a common mineral in planetary mantles, absorbs light around 1 micrometer, creating a distinctive spectral signature that helps scientists identify volcanic or impact-exposed materials. By studying the absorption patterns of reflected sunlight, we can map the composition of entire worlds without ever landing on them. Each mineral tells its story through the light it absorbs, through the specific energies its electrons accept as they jump between orbital levels. The moon's surface provides a particularly pure example because it lacks an atmosphere to complicate the signal. Lunar soil, or regolith, has been gardened by billions of years of meteorite impacts, which have melted, mixed, and darkened the surface materials. This process creates tiny glass spherules and agglutinates that absorb light more efficiently than fresh rock, making the moon darker than it would otherwise be. The absorption is so effective that the moon reflects only about 12% of the sunlight that hits it, despite being covered in light-colored minerals. The darkness comes from structure as much as composition. The microscopic texture of the regolith, full of tiny shadows and light-trapping geometries, enhances absorption. Ancient impacts have inadvertently created a surface optimized to capture light, and the moon glows more dimly because of it. Asteroids show an even wider range of absorption behaviors. Some, called C-type asteroids, are rich in carbon and absorb light so effectively that they reflect only 3 to 4% of incoming sunlight. Darker than asphalt, darker than coal. These objects are among the darkest natural surfaces in the solar system. Their darkness comes from carbonaceous materials, complex organic compounds that formed in the early solar system and have remained largely unchanged for billions of years. Other asteroids, the S-types, contain more silicate minerals and iron, and they reflect more light, though still absorbing the majority. A few rare asteroids, the M-types, are thought to be exposed metallic cores of shattered protoplanets, and they reflect light differently still, with metal's characteristic sheen. Each asteroid's absorption signature tells us about its history, its composition, and its place in the story of the solar system's formation. We can consider now the role of light absorption in the formation of planets themselves. In the early solar system, the protoplanetary disk surrounding the young sun was a swirling mixture of gas and dust. Dust grains absorbed starlight, warming slightly, and this warmth affected how they moved and interacted. Grains that absorbed more light experienced radiation pressure, the gentle push of photons that could alter their orbits. Grains that absorbed less were affected differently. Over time, grains collided and stuck together, growing into pebbles, boulders, and eventually planetesimals. The absorption of light played a subtle but real role in this process, influencing temperatures, affecting the condensation of different materials at different distances from the sun, and helping to determine which compounds remained solid and which evaporated. The inner solar system, warmer because of absorbed sunlight, became the realm of rocky planets. The outer solar system, where less light was absorbed and temperature stayed low, became the domain of ice and gas. Absorption helped draw the boundaries between worlds. Let us drift toward the phenomenon of light absorption in planetary rings, those delicate structures that encircle the gas giants. Saturn's rings, the most spectacular, are composed primarily of water-ice particles ranging from dust-sized grains to house-sized chunks. These particles are highly reflective in visible light, making the rings brilliant and beautiful. But they also absorb light, particularly in the infrared and ultraviolet. The absorbed energy causes very slight warming, which over time can sublime ice molecules from the particle surfaces. This process is extremely slow, but over millions of years it contributes to the evolution of the rings. Additionally, the rings absorb charged particles from Saturn's magnetosphere, and these particles can darken the ice by creating chemical changes. Some regions of the rings appear darker than others, partly because of this absorption-driven darkening. The rings are not static, they are slowly changing, and light absorption is one of the many processes shaping their evolution. Jupiter's rings, much fainter and composed largely of dust rather than ice, absorb light differently. The dust particles are thought to come from Jupiter's small inner moons, knocked loose by meteorite impacts. These particles are small enough that they absorb and scatter light in complex ways, and they don't reflect much visible light at all, which is why Jupiter's rings are so difficult to see. The absorption by these tiny grains is efficient, and the rings glow only faintly, mostly in scattered light. Uranus and Neptune also have rings, dark and narrow, composed of materials that absorb most incoming light. These rings are so dark that they were discovered only recently, and their composition remains somewhat mysterious. What we do know is that they absorb light far more effectively than they reflect it, making them nearly invisible except under specific observing conditions. Consider now the absorption of light by the surfaces of icy moons in the outer solar system. Europa, Jupiter's moon, has a surface of water ice that is relatively bright, but it's not pure white. Regions of the surface appear brownish or reddish, and this coloration is thought to come from salts, sulfur compounds, or organic materials brought up from the subsurface ocean through cracks in the ice. These materials absorb blue light more than red, creating the observed colors. The absorption signatures help scientists infer what chemicals might be present in Europa's hidden ocean, offering clues about the moon's potential habitability. Enceladus, Saturn's moon, is one of the brightest objects in the solar system, reflecting nearly all the sunlight that hits it. Its surface is fresh water ice, constantly renewed by geysers that spray material from the subsurface ocean into space. The freshness of the ice means there's been less time for darkening processes to occur, and absorption is minimal. The moon gleams like a polished gem, a testament to the power of geological activity to refresh a surface and reset its interaction with light. Titan, Saturn's largest moon, presents a completely different absorption environment. Its thick atmosphere, rich in nitrogen and methane, absorbs blue and ultraviolet light strongly, allowing only red and orange wavelengths to penetrate to the surface. This gives Titan's surface views of perpetual sunset quality, dim and orange, even at midday. The atmosphere also contains complex organic hazes, created by the interaction of methane and nitrogen under solar radiation. These hazes absorb light across many wavelengths, making Titan's atmosphere opaque in visible light. To see the surface, we must use infrared wavelengths where the atmosphere is more transparent. The Cassini spacecraft did exactly this, peering through the haze to map lakes of liquid methane and ethane, dunes of organic sand, and mountains of water ice. Titan's absorption environment is so effective that it has created a world hidden beneath a veil, where sunlight is filtered and softened before it ever touches the ground. Let us consider the absorption of light by volcanic materials, both on Earth and on other worlds. Fresh lava, when it first erupts, glows with its own thermal radiation, but as it cools, it becomes a dark, light-absorbing surface. Basalt, the most common volcanic rock, absorbs visible light efficiently, which is why lava fields appear black or dark gray. This absorption is due to iron-rich minerals within the rock, and it affects the local climate by changing how much sunlight is converted to heat. On Io, Jupiter's volcanically hyperactive moon, sulfur and sulfur dioxide coat the surface in yellows, reds, and whites. These materials have different absorption properties than basalt. Sulfur absorbs ultraviolet light and some blue wavelengths, contributing to the moon's colorful appearance. The volcanic plumes themselves absorb and scatter light, creating transient hazes visible from spacecraft. Io's surface is constantly being repaved by volcanic activity, and each new deposit brings a slightly different absorption signature, making the moon a dynamic, ever-changing canvas. We can turn our attention now to the absorption of light by organic materials in space, those carbon-based compounds that form the chemical foundation for life. Complex organic molecules, called tholins, are created when simple compounds like methane and nitrogen are exposed to ultraviolet light or charged particles. These tholins absorb light across a broad range of wavelengths, particularly in the blue and ultraviolet, giving them a characteristic reddish-brown color. They've been found on Titan, Pluto, Triton, and many other outer solar system bodies. They may also be present in comets and in the interstellar medium. Tholins are significant because they represent a step toward biological chemistry, a bridge between simple molecules and the complex compounds necessary for life. Their absorption properties tell us about their structure and composition, and by studying how they interact with light, we learn about the chemical pathways that might lead from sterile space to living worlds. Polycyclic aromatic hydrocarbons, or PAHs, are another class of organic molecules abundant in space. These are ring-shaped molecules made of carbon and hydrogen, and they absorb ultraviolet light very effectively. When they absorb a UV photon, they don't break apart. Instead, they vibrate and then re-emit the energy as infrared light. This makes PAHs both absorbers and emitters, and their infrared signatures are seen throughout the galaxy, in star-forming regions, planetary nebulae, and even in the diffuse interstellar medium. PAHs are thought to be among the most abundant organic molecules in the universe, and their interaction with light helps regulate the temperature of interstellar gas. They absorb harsh UV radiation, protecting other molecules from destruction, and they radiate infrared light that cools the gas, allowing it to collapse and form new stars. PAHs are cosmic mediators, absorbing and transforming light in ways that influence the very process of star formation. Let us consider the absorption of light in the context of photosynthesis, the process that powers most life on Earth. Plants, algae, and certain bacteria absorb light using pigments, most famously chlorophyll. Chlorophyll absorbs red and blue light strongly, but reflects green, which is why plants appear green to our eyes. The absorbed light provides the energy to split water molecules and combine carbon dioxide into sugars, storing the sun's energy in chemical form. This process is extraordinarily efficient in some ways. Chlorophyll can capture nearly every photon that strikes it in the right wavelength range, but it's also selective, leaving much of the solar spectrum unused. Some photosynthetic organisms use different pigments that absorb different wavelengths, allowing them to exploit light that chlorophyll-based life cannot. Purple bacteria, for example, use bacteria chlorophyll, which absorbs in the near-infrared. If we ever discover life on other planets, the absorption signatures of their photosynthetic pigments might be detectable from space, a biosignature written in the wavelengths they remove from their star's light. The absorption of light by photosynthetic organisms has shaped Earth's atmosphere and climate over billions of years. Early photosynthetic bacteria absorbed light and released oxygen as a waste product, gradually filling the atmosphere with this reactive gas. Oxygen itself absorbs ultraviolet light, leading to the formation of the ozone layer, which further altered the planet's absorption environment. The presence of life changed which wavelengths reach the surface, which in turn influenced the evolution of new forms of life adapted to those wavelengths. This is a feedback loop spanning geological time, where absorption by living organisms alters the environment, which alters the light available, which shapes the evolution of absorption strategies. Earth's current absorption environment, its atmospheric composition, surface colors, and distribution of life, is the product of billions of years of this coevolution between life and light. We can think about the absorption of light by water, the most common liquid on Earth, and a substance found throughout the solar system in frozen form. Liquid water is nearly transparent to visible light, which is why we can see through it, but it absorbs infrared and red light more strongly than blue. This is why deep water appears blue. The red wavelengths are absorbed within the first few meters, leaving only blue light to scatter back to our eyes. In the ocean, this absorption creates layers of color and temperature. Sunlight penetrates the surface, and the absorbed energy warms the upper layer, creating a thermocline, a boundary between warm surface water and cold deep water. This absorption-driven temperature structure affects ocean circulation, nutrient distribution, and marine life. Phytoplankton live near the surface where light is abundant, absorbing it for photosynthesis, and their presence can change the water's absorption properties, making it greener and altering how deeply light penetrates. The ocean is a layered system of absorption, each depth defined by which wavelengths can reach it and which have been captured above. Let us consider the absorption of light by clouds, those transient structures of water droplets and ice crystals suspended in the atmosphere. Clouds are highly reflective in visible light, which is why they appear white. They scatter all wavelengths roughly equally, but they also absorb light, particularly in the infrared. A thick cloud can absorb and re-emit infrared radiation, contributing to the greenhouse effect and affecting surface temperatures below. High, thin cirrus clouds absorb less and allow more infrared to escape to space, which can have a cooling effect. Low, thick stratus clouds absorb and reflect more, generally cooling the surface during the day by blocking sunlight. The absorption properties of clouds are complex and depend on droplet size, ice crystal shape, water content, and altitude. Clouds are one of the most difficult aspects of climate modeling because their absorption and reflection of light have such significant and variable effects on Earth's energy balance. On other planets, clouds absorb light in ways both familiar and strange. Venus's sulfuric acid clouds absorb ultraviolet light, which drives chemical reactions in the upper atmosphere. Jupiter's ammonia clouds absorb and scatter light differently depending on their altitude and composition. Titan's methane clouds absorb infrared light, affecting the Moon's already complex energy balance. Even Mars, with its thin atmosphere, occasionally forms water ice clouds that absorb and scatter light, creating halos around the Sun as seen from the surface. Clouds are universal features of planetary atmospheres, and wherever they form, they alter the absorption environment, changing how light interacts with the world below. We can turn now to the absorption of light by auroras, those shimmering curtains of color that appear near the poles of magnetized planets. Auroras occur when charged particles from the solar wind are funneled by a planet's magnetic field into the upper atmosphere, where they collide with atoms and molecules. These collisions excite the atoms, causing them to emit light. But before emission, there's absorption. The incoming particles carry energy, and when they strike an oxygen or nitrogen atom, that energy is absorbed, raising the atom to a higher energy state. The atom then releases this energy as a photon of a specific color, green or red for oxygen, blue or purple for nitrogen. The aurora is a dance of absorption and emission, energy transferred from the solar wind to atmospheric atoms and then released as visible light. The colors we see depend on which atoms are present, how much energy they absorb, and at what altitude the collisions occur. Earth's auroras are green and red primarily, while Jupiter's are dominated by ultraviolet light, invisible to human eyes but brilliant to spacecraft instruments. Let us consider the absorption of light by the human eye, the biological detector that allows us to perceive the universe. The retina contains two types of photoreceptor cells: rods, which are sensitive to low light levels but don't distinguish color, and cones, which detect color but require more light. Cones contain pigments that absorb specific wavelengths. One type absorbs blue light most strongly, another green, and another red. When a photon strikes a pigment molecule, it is absorbed, and the energy causes a change in the molecule's shape. This change triggers a cascade of chemical reactions that ultimately sends an electrical signal to the brain. The photon is absorbed and destroyed in the process, its energy transformed into neural information. Our perception of color, brightness, and form all begin with this act of absorption, with photons meeting molecules in the retina and ceasing to be light, becoming instead the foundation of vision and awareness. Different animals absorb light differently, seeing the world in ways we can barely imagine. Many birds have 4 types of cones instead of 3, including one that absorbs ultraviolet light, giving them a richer color perception than humans. Some fish have cones tuned to the specific wavelengths that penetrate to their ocean depth. Mantis shrimp have 16 types of photoreceptors, absorbing and distinguishing wavelengths across a vast range. Each species' visual system is optimized for its environment, absorbing the wavelengths that carry the most useful information. The absorption of light by eyes is not a passive process, but an evolutionary solution, a way of sampling the electromagnetic environment and extracting meaning from it. The absorption of light by black holes represents one of the most absolute forms of light capture in the universe. When a photon crosses the event horizon of a black hole, it cannot escape, no matter how energetic it might be. This is not absorption in the traditional sense, where energy transforms from one form to another within matter. Instead, it is a geometrical trap, a point of no return where space-time itself curves so steeply that all paths lead inward. The light simply vanishes from our observable universe, crossing into a region from which no information can return. It is a quiet, final disappearance, and in its own way, deeply restful to contemplate. Before reaching that horizon, light approaching a black hole experiences something extraordinary. The intense gravitational field stretches and redshifts the photons, pulling their wavelengths longer, draining their energy as they climb out of the gravity well. Light emitted near a black hole that manages to escape arrives at distant observers deeply reddened, transformed by the curvature of space. This gravitational redshift is a form of energy loss, a gentling of light as it struggles against gravity's pull. It is a reminder that even light, swift and weightless, feels the influence of mass. Around many black holes, swirling disks of hot gas and dust absorb and re-emit light in spectacular ways. These accretion disks glow brilliantly as material spirals inward, heated by friction and compression to millions of degrees. The atoms in these disks absorb photons, become excited, and then release new photons at different wavelengths. This cycle of absorption and emission creates the characteristic spectrum of an active black hole system. The light we see is not coming from the black hole itself, but from the matter falling toward it, matter that absorbs and transforms energy in its final moments before crossing the horizon. Neutron stars, the dense remnants of supernova explosions, also interact with light in remarkable ways. Their surfaces are so compact that a sugar cube-sized piece would weigh as much as all of humanity combined. The atoms at the surface are crushed into unusual states, and the intense magnetic fields warp the behavior of light itself. Photons passing near a neutron star can be bent by gravity, and light emitted from the surface is gravitationally redshifted as it escapes. The surface itself absorbs and emits radiation across the spectrum, from radio waves to X-rays, creating pulses we detect as the star rotates. Some neutron stars, called magnetars, possess magnetic fields 1,000 trillion times stronger than Earth's. These fields are so powerful they affect the vacuum of space itself, influencing how light propagates. Photons traveling through such intense fields can split into pairs of particles or have their polarization twisted. The surface of a magnetar absorbs high-energy radiation from the surrounding environment and from its own cooling interior, then releases bursts of X-rays and gamma rays. These are among the most energetic light absorption and emission processes in the universe, yet they happen in objects only about 20 kilometers across. White dwarfs, the quiet endpoints of stars like our Sun, also absorb light in subtle ways. These stellar remnants are supported not by fusion, but by electron degeneracy pressure, a quantum mechanical effect. Their surfaces are often covered in hydrogen or helium atmospheres, thin layers that absorb specific wavelengths of light. By studying which wavelengths are absorbed, astronomers can determine the composition and temperature of white dwarfs. Some white dwarfs have atmospheres polluted by rocky material from asteroids or planets that wandered too close and were torn apart. The absorption lines of calcium, iron, and other heavy elements reveal these quiet acts of cosmic consumption. Brown dwarfs occupy a middle ground between planets and stars. They are not massive enough to sustain hydrogen fusion, but they do glow faintly from the heat of their formation and, in some cases, from the fusion of deuterium. Their atmospheres contain complex molecules, water vapor, methane, ammonia, that absorb infrared light in intricate patterns. These absorption features allow us to study weather on brown dwarfs, to detect clouds of silicate or iron droplets drifting through their skies. The absorption of light in these dim, failed stars tells stories of chemistry and climate in objects that blur the line between planet and star. Comets, those icy wanderers from the outer solar system, absorb sunlight, and transform it into motion and spectacle. As a comet approaches the sun, solar radiation warms its surface, causing ices to sublimate directly into gas. This process absorbs energy from sunlight, turning photons into the kinetic energy of escaping molecules. The gas and dust released form the coma and tail, which then scatter and absorb more sunlight, glowing softly in the solar wind. The absorption of light by cometary material reveals its composition: water, carbon dioxide, methane, and organic compounds, offering clues to the chemistry of the early solar system. Asteroids, rocky remnants from the solar system's formation, absorb sunlight in ways that slowly alter their orbits. This effect, called the Yarkovsky effect, occurs because an asteroid absorbs sunlight on its day side and re-emits that energy as infrared radiation hours later, after the surface is rotated. This delayed emission creates a tiny thrust, gently pushing the asteroid in one direction. Over millions of years, this subtle absorption and re-emission of light can shift an asteroid's orbit significantly. It is a quiet reminder that even the absorption of light has momentum, has consequence. The surfaces of asteroids vary widely in their ability to absorb light. Some are dark and carbon-rich, absorbing most of the sunlight that strikes them and reflecting only a few percent. Others are brighter, made of metal or silicate rock, reflecting more light. By measuring how much light an asteroid absorbs versus reflects, its albedo, astronomers can infer its composition and history. Dark asteroids may be primitive, containing organic material unchanged since the solar system's birth. Bright asteroids may be fragments of differentiated bodies, once molten, now shattered and cold. Meteorites that fall to Earth carry the signature of light absorption in space. Their surfaces often bear fusion crusts, thin layers melted and darkened during their fiery passage through the atmosphere. But before that final plunge, these rocks drifted in space for millions or billions of years, absorbing cosmic rays and solar radiation. This absorption leaves traces: isotopic changes, radiation damage, darkening of minerals. By studying these effects, scientists can determine how long a meteorite was exposed to space, how far from the sun it traveled, and what kind of radiation environment it experienced. The zodiacal light, a faint glow visible in dark skies after sunset or before sunrise, arises from sunlight absorbed and scattered by interplanetary dust. These tiny particles, shed by comets and asteroids, fill the plane of the solar system. They absorb a small fraction of the sunlight that strikes them and scatter the rest, creating a soft, diffuse glow along the ecliptic. This absorption warms the dust slightly, and it re-emits that energy as infrared radiation, invisible to our eyes but detectable by instruments. The zodiacal light is a gentle reminder that space is not empty, but filled with dust that quietly interacts with light. Planetary rings, like those around Saturn, are arenas of constant light absorption and scattering. The ice particles that make up Saturn's rings are highly reflective, but they also absorb some sunlight, particularly in the ultraviolet and infrared. This absorbed energy warms the particles slightly, causing some ice to sublimate and creating a tenuous atmosphere around the rings. The absorption also varies with the composition of the particles. Those contaminated with rocky material or organic compounds absorb more light and appear darker. The delicate colors and brightness variations in Saturn's rings are maps of absorption, revealing the history of collisions, contamination, and evolution. Titan, Saturn's largest moon, has a thick atmosphere rich in nitrogen and methane. This atmosphere absorbs sunlight powerfully, particularly in the ultraviolet, where methane molecules break apart and recombine into complex organic compounds. These compounds form a haze that shrouds Titan's surface, absorbing even more light and giving the moon its characteristic orange color. The absorption of sunlight drives a complex chemistry in Titan's atmosphere, creating molecules found nowhere else in the solar system. It is a process both active and slow, transforming light into the building blocks of organic matter over millions of years. Europa, one of Jupiter's moons, has a surface of water ice that absorbs and reflects light in revealing ways. The ice is crisscrossed with dark streaks and patches, regions where subsurface material has been brought to the surface. These darker areas absorb more sunlight than the surrounding bright ice, and their absorption spectra suggest the presence of salts, sulfur compounds, or organic material. The absorption of light by Europa's surface is a window into the composition of the ocean that may lie beneath the ice, an ocean that could harbor life. Enceladus, a small moon of Saturn, sprays plumes of water vapor and ice particles into space from cracks in its south polar region. These plumes absorb and scatter sunlight, creating a faint glow detectable by spacecraft. The particles eventually fall back to the surface or escape into space, contributing to Saturn's E-ring. The absorption and scattering of light by these plumes have allowed scientists to study their composition, revealing water, salts, and organic molecules. The light absorbed by Enceladus's plumes connects the moon's hidden ocean to the observable universe. Mars, with its thin atmosphere and rusty surface, absorbs sunlight in ways that shape its climate and appearance. The red color of Mars comes from iron oxide in the dust and rocks, which absorbs blue and green light and reflects red. This absorption warms the surface during the day, and the heat is slowly released at night. Dust storms on Mars loft fine particles into the atmosphere, where they absorb sunlight and warm the air, sometimes intensifying the storm. The absorption of light by Martian dust is a key driver of the planet's weather and climate, a gentle but persistent force. The polar ice caps of Mars absorb sunlight seasonally, causing them to grow and shrink with the Martian year. In winter, carbon dioxide from the atmosphere freezes onto the caps, and in spring, sunlight absorbed by dust within the ice warms enough to sublimate the CO2 back into the atmosphere. This cycle of absorption and release drives winds and weather patterns across the planet. The absorption of light by Mars's ice caps is a clock, marking the rhythm of the seasons on a world far from the sun. Venus, shrouded in thick clouds of sulfuric acid, absorbs sunlight in complex ways. The clouds reflect most of the sunlight that strikes them, making Venus the brightest planet in our sky. But the clouds also absorb ultraviolet light, and within them, mysterious dark patches appear that absorb even more UV. These patches may be regions of different chemical composition or particle size, but their exact nature remains uncertain. Below the clouds, Venus's surface absorbs the small amount of sunlight that filters through, as well as the intense infrared radiation trapped by the greenhouse effect. The absorption of light on Venus is part of a runaway process that has made the planet's surface hot enough to melt lead. Mercury, the closest planet to the Sun, absorbs more sunlight per unit area than any other planet. Its surface is dark and heavily cratered, absorbing most of the intense solar radiation that strikes it. During the long Mercurian day, which lasts 176 Earth days, the surface temperature soars to over 400 degrees Celsius. At night, with no atmosphere to retain heat, the temperature plummets to minus 180 degrees. The absorption and re-emission of light on Mercury drive one of the most extreme temperature cycles in the solar system, a silent daily rhythm of heating and cooling. The Moon, Earth's companion, absorbs sunlight and glows softly in reflected light. Its surface is covered in regolith, a layer of dust and broken rock created by billions of years of meteorite impacts. This regolith is dark, absorbing about 90% of the sunlight that strikes it and reflecting only about 10%. The absorbed energy warms the surface during the lunar day, and that heat is slowly released during the long lunar night. Astronauts walking on the moon found that the surface dust, despite its darkness, could be surprisingly warm in sunlight and bitterly cold in shadow. The absorption of light by lunar regolith also creates a phenomenon called thermal moonquakes. As the sun rises over a lunar landscape, the surface warms and expands slightly. As it sets, the surface cools and contracts. These tiny expansions and contractions, driven by the absorption and loss of light energy, create stress in the rocks below, occasionally triggering small quakes. It is a gentle reminder that even on an airless, lifeless world, the absorption of light has mechanical effects, shaping and shifting the landscape over deep time. Earth's oceans absorb more sunlight than any other feature of our planet. Water is relatively transparent to visible light, especially blue and green wavelengths, allowing sunlight to penetrate tens or even hundreds of meters below the surface. This absorbed light warms the upper ocean, driving currents and weather patterns. Red and infrared light are absorbed within the first few meters, which is why underwater scenes appear blue. The red light has already been absorbed. The absorption of sunlight by the ocean is the primary engine of Earth's climate, storing and redistributing vast amounts of energy around the globe. Phytoplankton, tiny photosynthetic organisms drifting in the ocean, absorb sunlight and form the base of the marine food web. They contain chlorophyll, which absorbs red and blue light and reflects green, though in the ocean the overall effect makes chlorophyll-rich waters appear blue-green. These microscopic organisms absorb more sunlight than all the forests on land combined, producing about half of the oxygen in Earth's atmosphere. The absorption of light by phytoplankton is a quiet, essential process, one that connects the energy of the sun to nearly every living thing in the ocean. Coral reefs absorb and reflect light in ways that create their vibrant colors. The corals themselves are often pale, but they host symbiotic algae called zooxanthellae, which absorb sunlight for photosynthesis. The corals also produce fluorescent proteins that absorb blue light and re-emit it as green, red, or orange. This fluorescence may protect the algae from too much light or help them capture light in deeper water. The absorption and transformation of light in coral reefs creates some of the most colorful ecosystems on Earth, fragile and beautiful. Forests absorb sunlight through their leaves, and this absorption shapes the structure of the forest itself. The canopy absorbs most of the light, leaving the forest floor in shadow. Plants in the understory have adapted to absorb the limited light that filters through, often developing larger leaves or different pigments. The absorption of light by a forest also affects the local climate, as the energy is used for photosynthesis and transpiration, cooling the air and adding moisture. A forest is a layered system of light absorption, each level capturing what it can and passing the rest downward. Snow and ice absorb light differently depending on their purity and structure. Fresh, clean snow reflects most sunlight, which is why it appears so bright. But as snow ages, it can accumulate dust, soot, or algae, which absorb more light and cause the snow to darken and melt faster. Ice absorbs more light than snow because its crystals are larger and allow light to penetrate deeper before scattering back out. Blue ice, found in glaciers and icebergs, appears blue because it absorbs red light as the light travels through the ice, leaving only blue to emerge. The absorption of light by snow and ice is a key factor in Earth's albedo and climate. Deserts absorb sunlight intensely during the day, and their surfaces can become hot enough to burn skin. Sand and rock absorb visible and infrared light, and because deserts have little vegetation or moisture, most of that absorbed energy goes into heating the ground. At night, with clear skies and dry air, the heat radiates away quickly, and deserts can become surprisingly cold. The absorption and release of light in deserts create extreme temperature swings, shaping the life and landscape of these arid regions. Volcanic rock, freshly erupted, is often dark and absorbs sunlight efficiently. Basalt, the most common volcanic rock, is black or dark gray, and it warms quickly in the sun. Over time, weathering and the growth of lichens and plants can change the surface, altering its absorption properties. In Iceland, fields of black lava rock absorb so much sunlight that they can be warm to the touch, even on cool days. The absorption of light by volcanic landscapes is part of the process of soil formation, as the warmth encourages the breakdown of rock and the colonization by life. Clouds absorb and scatter sunlight, and their effect on Earth's climate is complex. Bright, thick clouds reflect most sunlight back to space, cooling the planet. Thin, high clouds absorb infrared radiation from the surface and re-emit it, warming the planet. The balance between these effects depends on the type, altitude, and thickness of the clouds. The absorption of light by clouds is one of the largest uncertainties in climate science, a reminder that even common phenomena can be deeply intricate. Aerosols, tiny particles suspended in the atmosphere, absorb and scatter light in ways that affect climate and visibility. Some aerosols, like sulfate particles from volcanic eruptions, reflect sunlight and cool the planet. Others, like black carbon from fires and combustion, absorb sunlight and warm the atmosphere. The absorption of light by aerosols can also change the color of the sky, creating hazy or reddish tones. These particles are small, often just a few micrometers across, but their collective absorption of light has global effects. The absorption of light by the atmosphere creates the colors of twilight. After the sun sets, the sky remains bright because the upper atmosphere is still illuminated. The atmosphere absorbs and scatters this light, and the colors change as the sun sinks deeper below the horizon. First, the sky glows orange and pink, then purple, then deep blue. This progression reflects the changing path of sunlight through the atmosphere and the wavelengths that are absorbed or scattered at each stage. Twilight is a slow, gentle demonstration of atmospheric absorption, a daily gift of color and calm. The green flash, a rare optical phenomenon, occurs when the sun is just below the horizon and atmospheric refraction and absorption combine to isolate a brief flash of green light. The atmosphere absorbs red and yellow light more strongly at such low angles, and refraction spreads the sun's image into a spectrum. For a moment, only the green part of the spectrum is visible. It is a fleeting event, lasting only a second or two, and it requires a clear horizon and calm air. The green flash is a reminder that the absorption of light can create moments of unexpected beauty. Auroras, though primarily emission phenomena, also involve absorption. When charged particles from the solar wind strike the upper atmosphere, they excite oxygen and nitrogen atoms, which then emit light. But these same particles and the light they produce can also be absorbed by other atoms and molecules in the atmosphere. The absorption and re-emission of energy in auroras create the shifting curtains and rays of color that dance across polar skies. It is a cycle of energy, absorbed and released, painting the night with green, red, and purple light. The absorption of light by the ionosphere affects radio communication. The ionosphere is a layer of the atmosphere where solar radiation has ionized atoms, creating free electrons. These electrons can absorb and reflect radio waves, allowing some frequencies to bounce around the Earth and enabling long-distance communication. The absorption varies with the time of day, the season, and solar activity. At night, when the sun's light is no longer ionizing the atmosphere, absorption decreases and some frequencies propagate more easily. The absorption of light by the ionosphere is invisible to our eyes, but it shapes the way we communicate across the globe. The absorption of light by DNA can cause mutations. Ultraviolet light, particularly UVB and UVC, is absorbed by the molecular bonds in DNA and this absorbed energy can cause adjacent thymine bases to link together, forming dimers. These dimers distort the DNA structure and can lead to errors during replication. Cells have repair mechanisms to fix this damage, but if the damage is extensive or the repairs fail, mutations can occur. This is why UV exposure is linked to skin cancer. The absorption of light by DNA is a molecular event with profound biological consequences. Plants have evolved mechanisms to manage the absorption of light. Too much light can damage the photosynthetic machinery, so plants can dissipate excess absorbed energy as heat, a process called non-photochemical quenching. They can also move their chloroplasts within cells to avoid intense light, or angle their leaves to reduce absorption. Some plants produce pigments that absorb UV light, protecting the underlying tissues. The absorption of light by plants is not passive. It is actively regulated, a balance between capturing enough energy and avoiding damage. The absorption of light by pigments in animal eyes enables vision. In the retina, photoreceptor cells contain pigments like rhodopsin, which absorbs light and triggers a cascade of chemical reactions that generate a neural signal. Different pigments absorb different wavelengths, allowing color vision. The absorbed light is converted into information, into the perception of the world. This absorption is extraordinarily efficient. A single photon can be enough to trigger a response in a rod cell under dark adapted conditions. The absorption of light by the eye is the bridge between the physical world and conscious experience. Some animals can see wavelengths of light that humans cannot, because they have pigments that absorb in the ultraviolet or infrared. Bees, for example, can see UV light, which helps them locate nectar guides on flowers, patterns invisible to us. Some snakes can sense infrared radiation, absorbing it with specialized pit organs to detect the body heat of prey. The absorption of light by these sensory systems expands the perceptual world of these animals, revealing patterns and information hidden from human eyes. The absorption of light by melanin, the pigment in skin, hair, and eyes, protects against UV damage. Melanin absorbs UV radiation and dissipates the energy as harmless heat, reducing the amount that reaches deeper tissues and DNA. People with more melanin in their skin have greater protection from UV light, which is why skin color varies with ancestral exposure to sunlight. The absorption of light by melanin is an evolutionary adaptation, a shield shaped by the sun's radiation over countless generations. The absorption of light by chlorophyll in leaves changes with the seasons. In autumn, as days shorten and temperatures drop, many trees stop producing chlorophyll. The green pigment breaks down, and its absorption of red and blue light ceases. This reveals other pigments, carotenoids and anthocyanins, that absorb different wavelengths and reflect yellows, oranges, and reds. The brilliant colors of fall foliage are a result of changing patterns of light absorption, a quiet, annual transformation driven by the angle of the sun and the rhythm of the year. The absorption of light by water in plant cells maintains turgor pressure, the rigidity that keeps plants upright. Water molecules absorb infrared radiation, and this absorbed energy contributes to the kinetic energy of the molecules, affecting temperature and evaporation. As water evaporates from leaves, it draws more water up from the roots, a process powered indirectly by the absorption of light during photosynthesis. The absorption of light by plants is connected to their structure, their growth, and their ability to stand tall and reach toward the sun. The absorption of light by ancient pigments tells us about life in the deep past. Some rocks contain chemical fossils, molecules derived from chlorophyll or other pigments that absorbed light billions of years ago. By analyzing these molecules, scientists can infer what kinds of photosynthetic organisms existed and what wavelengths of light they absorbed. This is a form of paleobiology written in absorption, a record of how life captured sunlight long before animals, before forests, before even oxygen filled the air. The absorption of light by interstellar molecules can create masers, the microwave equivalent of lasers. In some regions of space, molecules like water or methanol absorb energy from nearby stars or shock waves, and the molecules become excited. Under the right conditions, they release this energy coherently, all at the same wavelength and in phase, creating an intense beam of microwave radiation. Masers are rare and require specific conditions, but they are natural demonstrations of stimulated emission, a quantum process driven by the absorption and release of light. The absorption of light by exoplanet atmospheres has revealed the presence of water, methane, carbon dioxide, and even hints of more complex molecules. When an exoplanet transits its star, some of the starlight passes through the planet's atmosphere, and molecules in that atmosphere absorb specific wavelengths. By comparing the spectrum of the star with and without the planet in front, astronomers can identify absorption features and infer the atmospheric composition. This technique, called transmission spectroscopy, has opened a new era in the study of distant worlds, allowing us to sample their air from light years away. Some exoplanets are so hot that their atmospheres contain vaporized metals, sodium, potassium, iron, that absorb light at characteristic wavelengths. These hot Jupiters orbit very close to their stars, and their day sides can reach temperatures of thousands of degrees. The absorption of light by metal vapor in these atmospheres creates strong spectral lines, which have been detected from Earth and space. It is a strange and extreme form of atmospheric absorption, a reminder that planets come in varieties we never imagined before we could study them directly. The search for life on other planets often focuses on biosignatures, chemicals in an atmosphere that might indicate biological activity. Oxygen, ozone, and methane in certain combinations could suggest life, because these gases absorb light at specific wavelengths and are difficult to maintain together without biological processes. The absorption of light by an exoplanet's atmosphere could one day reveal the presence of life beyond Earth, a profound discovery written in the language of absorbed photons. The absorption of light by cosmic dust affects our view of the universe, but also creates beauty. Dust lanes and spiral galaxies absorb light from stars behind them, creating dark ribbons across the bright disk. These lanes trace the spiral arms, where dust and gas are densest, and where new stars are forming. The absorption of light by dust is not an obstacle. It is a map, showing us where matter is concentrated and where the future of the galaxy is being shaped. The absorption of light by human skin is a story written in layers, each responding differently to the wavelengths that reach us. The outermost layer, the epidermis, contains melanin granules that absorb ultraviolet light, protecting the deeper tissues from damage. This absorption is not uniform across all people. Melanin concentration varies, creating the beautiful spectrum of human skin tones, each adapted to different intensities of sunlight across our planet's latitudes. Beneath the epidermis, the dermis contains blood vessels whose hemoglobin absorbs green and blue light, giving our skin its warm undertones. When light penetrates skin, some is absorbed, some is scattered, and some reflects back to create the colors we see. This interaction is so gentle, so constant, that we rarely notice it, yet it connects us directly to the same photons that have traveled across space, absorbed by dust and gas, before finally reaching us here. The absorption of light by snow and ice tells a story of subtle transformation over time. Fresh snow appears brilliantly white because it reflects most visible light, but even snow absorbs a small fraction of the photons that strike it. This absorption is strongest in the infrared, where the molecular vibrations of water crystals match the energy of incoming photons. As snow ages, as it compacts and accumulates dust, its absorption increases. Darker particles embedded in snow absorb sunlight and warm their surroundings, causing the snow to melt faster than it would if pure. In polar regions, this feedback loop is delicate but significant. Small changes in absorption can accelerate melting, which exposes darker land or ocean beneath, which absorbs even more light. The process is slow, patient, unfolding across seasons and years, a quiet conversation between light and ice that shapes the climate of our world. The absorption of light by volcanic rock preserves a record of ancient eruptions and the minerals formed in fire. Basalt, the dark rock that covers ocean floors and forms shield volcanoes, is rich in iron and magnesium, elements that absorb visible light strongly, giving the rock its deep gray or black color. When sunlight strikes basalt, the photons are absorbed by the electronic transitions in iron ions, converting light energy into heat. Over millions of years, this absorbed energy contributes to the weathering of rock, breaking down minerals and releasing nutrients into soil. On other worlds, volcanic rocks tell similar stories. The dark plains of the moon, the ancient lava flows on Mars, the volcanic surface of Io, constantly renewed by eruptions. Each absorbs light in its own way. Each carries the signature of the processes that formed it, and each slowly changes under the steady gaze of the sun. The absorption of light by interplanetary dust creates a faint glow in the night sky, known as the zodiacal light. This dust, left behind by comets and asteroids, orbits the sun in a flattened disk that lies along the plane of the solar system. When sunlight strikes these tiny particles, some light is absorbed and re-emitted as heat, while some is scattered toward Earth. The absorbed light warms the dust grains slightly, causing them to spiral slowly inward toward the sun over millions of years, a process called the Poynting-Robertson effect. This effect is so gentle that a single grain takes eons to fall, yet it ensures that the zodiacal dust cloud is constantly replenished by new material. The glow is faint, best seen from dark locations after twilight fades, a soft pyramid of light rising from the horizon, a visible reminder of the dust that fills our solar system and the quiet absorption that shapes its destiny. The absorption of light by amino acids and other organic molecules may have played a role in the origin of life on Earth. Ultraviolet light from the young sun struck the early atmosphere and surface, where simple molecules absorbed photons and underwent chemical reactions. Some of these reactions created more complex molecules, including the building blocks of proteins and nucleic acids. Certain amino acids absorb ultraviolet light strongly, and this absorption can drive the formation of peptide bonds, linking amino acids into chains. In this way, the absorption of light may have been one of the energy sources that powered prebiotic chemistry, transforming simple compounds into the intricate molecules that eventually became life. The process was random, inefficient, spread across millions of years in countless environments, yet it worked. The same absorption that protects us now may have helped create us in the first place, a quiet paradox written in the language of photons and molecules. The absorption of light by desert sand creates the intense heat that defines arid landscapes. Sand grains, composed mostly of quartz and feldspar, absorb visible and infrared light, converting photon energy into thermal energy. Because sand has low heat capacity and poor conductivity, the absorbed energy raises the surface temperature dramatically during the day. In some deserts, sand surfaces can reach temperatures above 60 degrees Celsius, hot enough to cause burns. At night, the same sand radiates this heat away into the clear, dry air, cooling rapidly under the stars. This cycle of absorption and emission shapes desert climates, creating extreme temperature swings and driving the winds that sculpt dunes and carry dust across continents. The absorption is simple, direct, yet its effects ripple outward, influencing weather patterns and ecosystems across vast regions. The absorption of light by the pigments in autumn leaves reveals colors that were hidden all summer long. Chlorophyll, the dominant pigment during the growing season, absorbs red and blue light so strongly that it masks the presence of other pigments. But as days shorten and temperatures drop, trees break down their chlorophyll to reclaim its nutrients, and the green fades away. Beneath, carotenoids absorb blue and green light, reflecting yellow and orange. Anthocyanins, produced in response to bright light and cool temperatures, absorb green and yellow, reflecting red and purple. Each pigment absorbs a different set of wavelengths, and together they create the brilliant tapestry of fall foliage. The colors are not new. They were there all along, quietly absorbing light in the shadow of chlorophyll, waiting for their moment to be seen. It is a gentle reminder that absorption is not just about what is taken away, but also about what is revealed. The absorption of light by interstellar hydrogen at specific wavelengths creates the Lyman alpha forest, a pattern seen in the spectra of distant quasars. As light from a quasar travels toward us, it passes through clouds of hydrogen gas scattered along the way. Each cloud absorbs light at the wavelength corresponding to the Lyman alpha transition, the energy needed to excite a hydrogen electron from its ground state to the first excited state. Because the universe is expanding, each cloud is moving away from us at a different speed, and the Doppler effect shifts the absorption to a slightly different wavelength for each cloud. The result is a series of absorption lines, a forest of dark features in the spectrum, each marking a hydrogen cloud billions of light years away. By studying this forest, astronomers can map the distribution of gas in the early universe, trace the growth of cosmic structure, and measure the expansion rate across time. It is a quiet archive, written in absorbed photons, preserving the history of matter across the cosmos. The absorption of light by iron in Earth's core is a process we can only infer, never directly observe. The core lies nearly 3,000 kilometers beneath our feet, beyond the reach of drills or cameras. Yet we know it is there from seismic waves and gravitational measurements. If light could somehow reach the core, the iron and nickel there would absorb it strongly, particularly at shorter wavelengths. The core is hot, over 5,000 degrees Celsius, and it glows with thermal radiation. Though this light is trapped, absorbed and re-emitted countless times by the surrounding mantle and crust before any hint of it could escape. The core's energy does reach the surface, but as heat conducted slowly upward over millions of years, driving plate tectonics and volcanic activity. The absorption of light within the Earth is part of a vast thermal engine, invisible, patient, shaping the surface world through processes that unfold in deep darkness. The absorption of light by protoplanetary disks around young stars determines where planets can form and what they will be made of. Close to the star, intense ultraviolet invisible light heats the disk, keeping volatile materials like water and methane in gaseous form. These gases absorb light and re-radiate it as infrared, but they cannot condense into solid particles, so only rocky materials can accumulate into planets in the inner disk. Farther out, beyond the snow line, temperatures drop low enough for water ice to form, and the absorption of light by ice grains changes the disk's behavior. Ice-coated particles stick together more easily, allowing planets to grow larger and faster. The absorption of starlight, therefore, sets the boundary between rocky worlds and gas giants, between inner and outer solar systems. It is a quiet sorting process, driven by the wavelengths of light and the materials that absorb them, playing out over millions of years as planets slowly gather from dust. The absorption of light by cosmic rays is a subtle process, because cosmic rays are not light, but high-energy particles, protons, electrons, and atomic nuclei traveling near the speed of light. However, when these particles collide with gas or dust in space, they can produce gamma rays, the highest energy form of light. These gamma rays can then be absorbed by matter, just like any other photon, though their high energy means they penetrate deeply before being stopped. In dense regions like molecular clouds, gamma rays produced by cosmic ray collisions are absorbed by the surrounding gas, heating it slightly and ionizing atoms. This creates a faint glow of lower energy light, a secondary emission that reveals the presence of cosmic rays even when the rays themselves are invisible. The absorption of gamma rays is a quiet intermediary, a way the universe converts the energy of fast particles into the warmth and light of interstellar space. The absorption of light by spider webs is a small, delicate phenomenon, yet it reveals the intricate structure of silk. Spider silk is composed of proteins arranged in crystalline and amorphous regions, and these regions absorb and scatter light differently. Some spider webs appear nearly invisible, reflecting and transmitting most light, which helps them remain hidden from prey. Others, especially those spun by orb-weaving spiders, include silk threads coated with sticky droplets that scatter light, making the web shimmer in the sun. The silk itself absorbs ultraviolet light weakly, and some spiders incorporate UV-reflective silk into their webs, creating patterns visible to insects but not to human eyes. The absorption and reflection of light by silk is tuned by evolution, a quiet optimization that balances visibility and invisibility, attraction and concealment, all in threads thinner than a human hair. The absorption of light by distant supernovae allows astronomers to measure the expansion of the universe. When a white dwarf star explodes as a type I supernova, it briefly outshines its entire galaxy, emitting light across all wavelengths. As this light travels toward us, it passes through intergalactic space, and some of it is absorbed by intervening gas and dust. But more importantly, the expansion of space itself stretches the light, shifting it toward longer, redder wavelengths, a process called cosmological redshift. By measuring how much the supernova's light has been redshifted and comparing it to the supernova's intrinsic brightness, astronomers can calculate how far away it is and how fast space is expanding. The absorption lines in the supernova spectrum, caused by elements in the expanding debris, provide additional information about the explosion and the material it passes through. It is a method of measuring the universe that relies on the quiet absorption and stretching of light across billions of years, a cosmic ruler written in photons. The absorption of light by feathers gives birds their extraordinary colors, through both pigments and structural effects. Melanin, the same pigment found in human skin, absorbs most wavelengths and creates blacks, browns, and grays. Carotenoids, obtained from diet, absorb blue and green light, producing yellows, oranges, and reds. But some of the most brilliant bird colors come not from absorption, but from microscopic structures in feathers that scatter light in specific ways. The blue of a jay's feather, for example, is created by structures that scatter short wavelengths while absorbing longer ones. The iridescence of a hummingbird's throat comes from layered structures that interfere with light, changing color depending on the angle of view. In these cases, absorption works together with scattering and interference, removing certain wavelengths to enhance others, creating colors more vivid than pigments alone could produce. It is a collaboration between chemistry and physics, between molecules and structures, all to capture and control the light that makes birds visible to each other and to us. The absorption of light by glacial ice reveals the history of Earth's climate, preserved in layers that stretch back hundreds of thousands of years. Each year, snow falls on polar ice sheets and compresses into ice, trapping tiny bubbles of ancient air. As the ice accumulates, it forms a record of past atmospheres, with each layer corresponding to a specific year. Scientists drill cores from these ice sheets and analyze the ice and the air bubbles within. The ice itself absorbs infrared light in patterns that depend on the isotopes of oxygen and hydrogen it contains, and these isotopes reveal the temperature when the snow fell. Dust and volcanic ash trapped in the ice absorb light differently, marking events like eruptions and dust storms. By studying how ice absorbs light and what is trapped within it, researchers can reconstruct climates from ages long before humans walked the Earth. The absorption is a silent witness, holding the memory of warmth and cold, of calm and catastrophe, written in frozen water. The absorption of light by the surfaces of neutron stars creates absorption lines that reveal the intense gravitational fields around these objects. Neutron stars are so dense that a sugar cube-sized piece would weigh as much as all of humanity. Their surfaces are made of iron and other heavy elements, compressed into crystalline structures unlike anything on Earth. When light from the hot surface tries to escape, it must climb out of a deep gravitational well, losing energy in the process, a phenomenon called gravitational redshift. Atoms in the star's thin atmosphere absorb light at specific wavelengths, creating absorption lines in the spectrum. But the intense gravity shifts these lines, stretching them toward the red. By measuring the amount of shift, astronomers can calculate the star's mass and radius, testing our understanding of matter at extreme densities. The absorption lines are faint, distorted by gravity and Doppler shift from the star's rapid rotation. Yet they carry information from one of the most extreme environments in the universe, a place where space-time itself bends light and time. The absorption of light by morning dew on grass is a fleeting, everyday miracle. Each droplet acts as a tiny lens, focusing sunlight and absorbing some wavelengths while scattering others. The water absorbs infrared light, warming slightly as the sun rises. Visible light passes through the droplet, refracts, and sometimes reflects internally, creating brief sparkles and rainbow glints. Chlorophyll in the grass beneath absorbs red and blue light, even through the water, continuing photosynthesis as soon as the sun appears. The dew itself is temporary. Within an hour or two, the absorbed energy evaporates the droplets, returning water to the air. This daily cycle of condensation, absorption, and evaporation is part of the hydrological cycle, moving water from soil to air to plant and back again. The absorption of light by dew is small, local, transient, yet it is repeated across millions of square kilometers every morning, a quiet ritual that connects the energy of the sun to the water that sustains life. The absorption of light by the event horizons of black holes is the ultimate endpoint for photons that venture too close. Once light crosses the event horizon, it can never escape. Not because it is absorbed in the traditional sense, but because space-time itself is so warped that all paths lead inward. From the perspective of a distant observer, light approaching the event horizon appears to slow down, redshift, and fade, as if being absorbed gradually. But for the photon itself, if we could follow its journey, it simply continues inward at the speed of light until it reaches the singularity, a point where our understanding of physics breaks down. The absorption is absolute, final, and yet it adds to the black hole's mass and energy, contributing to its gravity and its ability to warp space-time further. In this way, even absorbed light is not truly lost. It becomes part of the black hole, woven into the fabric of the cosmos in a form we can measure but not see. The absorption of light by the wings of butterflies is a study in precision and beauty. Butterfly wings are covered with thousands of tiny scales, each shaped and structured to interact with light in specific ways. Pigments within the scales absorb certain wavelengths. Melanins create browns and blacks. Pterins produce whites and yellows. Homochromes generate reds and oranges. But many of the most striking butterfly colors come from structural effects, where microscopic ridges and layers on the scales interfere with light. These structures absorb some wavelengths while reflecting others in brilliant, iridescent hues. The blue morpho butterfly, for example, has no blue pigment. Its wings absorb red, yellow, and green light, while structures scatter blue light intensely. The scales are arranged in overlapping rows, like shingles on a roof, and each scale is a tiny masterpiece of absorption and reflection. When a butterfly flies, the angle of light changes constantly, and the colors shift and shimmer, a living display of how absorption shapes what we see. The absorption of light by Saturn's rings reveals their composition and the processes that shape them. The rings are made mostly of water ice, with small amounts of rocky material and organic compounds. Ice reflects visible light strongly, making the rings bright and white, but it absorbs infrared light, especially at wavelengths corresponding to the vibrations of water molecules. By measuring how much light is absorbed at different wavelengths, scientists can determine the purity of the ice, the size of the particles, and the presence of contaminants. Regions of the rings that appear redder absorb blue light more strongly, indicating the presence of organic molecules or iron-rich dust. The absorption also reveals the temperature of the ring particles, which hover around -200 degrees Celsius. Over time, absorbed sunlight causes ice to sublimate slowly, and the rings lose mass, a process that suggests they may be relatively young, perhaps only a few 100 million years old. The rings are not eternal. They are slowly fading, and the absorption of light is one of the quiet forces driving their evolution. The absorption of light by human tears is a small, intimate process, yet it connects us to the same physics that governs oceans and atmospheres. Tears are mostly water, with small amounts of salts, proteins, and lipids. Water absorbs infrared light, which is why tears feel warm when they fall. The proteins and lipids scatter visible light slightly, which can make tears appear faintly cloudy, though usually they are clear. When light passes through a tear on the surface of the eye, some is absorbed, some is refracted, and some continues into the eye to be absorbed by the retina. Tears also protect the eye by absorbing ultraviolet light, preventing it from reaching the delicate tissues beneath. The absorption is gentle, constant, and essential. Without the thin film of tears, our eyes would dry out and our vision would blur. In this way, the absorption of light by tears is part of the act of seeing, a quiet layer of protection and clarity that we carry with us always. The absorption of light by ancient amber preserves the colors and forms of life from millions of years ago. Amber is fossilized tree resin, and it often contains trapped insects, plant fragments, and even bubbles of ancient air. The resin absorbed certain wavelengths of light when it was fresh, giving a golden or orange hue, and this color deepens over time as the resin polymerizes and oxidizes. Inclusions within the amber, such as the body of an insect, absorb light differently, creating contrast that makes them visible. Some amber fluoresces under ultraviolet light, absorbing UV photons and re-emitting visible light in blues and greens, a property caused by organic compounds within the resin. By studying how amber absorbs light, scientists can learn about the chemistry of ancient forests, the evolution of insects, and even the composition of the atmosphere in which the resin formed. The absorption is a window into deep time, a way of seeing the past through the light that ancient materials captured and held. The absorption of light by the soil beneath our feet is the foundation of terrestrial ecosystems. Soil is a mixture of minerals, organic matter, water, and air, and each component absorbs light differently. Dark soils, rich in organic matter, absorb most visible and infrared light, warming quickly in the sun. Light-colored soils, high in sand or clay, reflect more light and stay cooler. The absorbed energy drives evaporation, warms the air above, and powers the decomposition of organic matter by microbes. Plant roots grow in soil, and though they are in darkness, they depend on the warmth and water that absorbed sunlight provides. The absorption of light by soil is one of the ways solar energy enters the biosphere, transformed from photons into heat, into movement, into life. It is a quiet process, hidden beneath leaves and grass, yet it shapes the temperature, moisture, and fertility of the ground, influencing everything that grows. The absorption of light by the canopy of a rainforest creates a layered world of light and shadow. At the top, the emergent trees absorb intense sunlight, their leaves packed with chlorophyll. Below, the canopy layer absorbs most of the remaining light, leaving only a few percent to filter down to the understory. By the time light reaches the forest floor, it is dim, green-tinted, and diffuse, absorbed and scattered by countless leaves above. Plants on the forest floor have adapted to this low light, with large leaves and high concentrations of chlorophyll to capture every available photon. The absorption of light by the canopy also cools the air below, creating a humid, stable microclimate that supports an incredible diversity of life. The vertical structure of the forest is shaped by light absorption. Each layer receives a different quality and quantity of light, and each supports a different community of plants, animals, and fungi. It is a hierarchy built on photons, a tower of life constructed from absorbed sunlight. The absorption of light by the human brain is indirect, yet essential for consciousness and perception. The brain itself does not absorb light. It is enclosed in darkness within the skull. But the information carried by light, absorbed by the retina, and converted into electrical signals, travels along the optic nerve to the visual cortex at the back of the brain. There, neurons process the signals, constructing the images we see, the colors we perceive, the motion we track. The brain uses about 20% of the body's energy, much of it devoted to processing visual information. In a sense, the absorption of light by the retina is the first step in a chain that ends with thought, with recognition, with memory. The photons that strike our eyes are absorbed and transformed, their energy converted into the neural activity that allows us to see the stars, the faces of loved ones, the words on a page. It is a transformation so seamless that we forget it is happening. Yet it is one of the most profound processes in the universe, the conversion of light into awareness. The absorption of light by distant galaxies reveals their motion, their composition, and their history. When we observe a galaxy, we see the combined light of billions of stars, along with emission and absorption from gas and dust. The absorption lines in a galaxy's spectrum tell us which elements are present in its stars and interstellar medium. By measuring the Doppler shift of these lines, we can determine whether the galaxy is moving toward us or away, and how fast. Most galaxies are moving away, their light redshifted by the expansion of space, and the farther away they are, the faster they recede. The absorption of light by dust within the galaxy dims and reddens the light, an effect that must be corrected to measure the galaxy's true brightness and distance. By studying absorption in galaxies across the universe, astronomers can trace the history of star formation, the enrichment of gas with heavy elements, and the growth of structure over cosmic time. Each absorbed photon is a clue, a piece of a story that stretches across billions of years. The absorption of light by frost on a winter morning transforms landscapes into glittering fields of white. Frost forms when water vapor in the air deposits directly onto cold surfaces, creating delicate crystals of ice. These crystals absorb infrared light, warming slightly as the sun rises, but they reflect most visible light, making frost appear bright and white. The absorbed energy causes the frost to sublimate, turning directly from solid to vapor without melting, a process that happens quickly once the sun is up. The patterns of frost, feathery, branching, intricate, are shaped by the way ice crystals grow and by the tiny variations in temperature and humidity across a surface. The absorption of light by frost is a transient phenomenon, lasting only until the warmth of the day erases it. But it is repeated every winter morning in temperate and polar regions, a quiet cycle of freezing and thawing, of light absorbed and released. The absorption of light by the pigments in our food connects us directly to the energy of the sun. Fruits and vegetables get their colors from pigments that absorb specific wavelengths. Chlorophyll in greens, carotenoids in oranges and yellows, anthocyanins in reds and purples. When we eat these foods, we consume the molecules that absorb sunlight, and our bodies break them down to release the stored energy. Carotenoids, for example, are converted into vitamin A, essential for vision and immune function. The absorption of light by plants is the beginning of the food chain, and every meal we eat is, in a sense, a meal of sunlight, transformed and concentrated by the quiet work of photosynthesis. The energy that powers our muscles, our thoughts, our heartbeat, all comes from photons absorbed by leaves and converted into chemical bonds, then passed through the web of life until it reaches us. The absorption of light by the atmosphere of Titan, Saturn's largest moon, creates a thick orange haze that hides the surface from view. Titan's atmosphere is mostly nitrogen, with a small amount of methane. High in the atmosphere, ultraviolet light from the sun breaks apart methane molecules, and the fragments recombine into complex organic compounds called tholins. These tholins absorb blue and ultraviolet light strongly, scattering red and orange light, which gives Titan its distinctive color. The absorbed energy drives a rich photochemistry, producing a variety of hydrocarbons and nitriles that rain down onto the surface. The haze is so thick that only infrared light and radio waves can penetrate it easily, which is why the Cassini spacecraft used radar to map Titan's surface. The absorption of light by Titan's atmosphere is a window into prebiotic chemistry, a laboratory where sunlight transforms simple molecules into the building blocks of life, under conditions that may resemble the early Earth. The absorption of light by the surface of the moon has been measured by astronauts and instruments left behind during the Apollo missions. The moon's regolith, the layer of dust and broken rock that covers the surface, absorbs most of the sunlight that strikes it, reflecting only about 12%. This low reflectivity, called albedo, is due to the presence of iron and titanium oxides in the lunar soil, which absorb visible light strongly. The absorbed energy heats the surface to over 100 degrees Celsius during the lunar day. At night, with no atmosphere to retain heat, the surface cools rapidly, dropping to minus 170 degrees. The absorption of light by the moon also affects its orbit, very slightly. Absorbed sunlight exerts a tiny pressure, and the re-emission of heat as infrared light creates a subtle thrust, a process called the Yarkovsky effect. Over millions of years, this can change the moon's orbit by small amounts, a reminder that even the absorption of light has consequences that accumulate over time. The absorption of light by clouds is one of the most important factors in Earth's climate, yet it is also one of the most uncertain. Clouds reflect sunlight back to space, cooling the planet, but they also absorb and emit infrared radiation, trapping heat. The balance between these two effects depends on the type, altitude, and thickness of the clouds. High, thin cirrus clouds absorb little sunlight but trap a lot of infrared, warming the planet. Low, thick stratocumulus clouds reflect a lot of sunlight but trap less infrared, cooling the planet. The absorption of light by water droplets and ice crystals in clouds depends on the size and shape of the particles, and on the wavelength of the light. Climate models must account for these complexities to predict how the planet will respond to rising greenhouse gas levels. And small changes in cloud cover or cloud properties can have large effects on global temperature. The absorption of light by clouds is a delicate, dynamic process, constantly shifting with weather and season, a key variable in the fate of our climate. And now, as we draw near the end of this long, gentle journey through the absorption of light, let's take a moment to reflect on what we have explored together. We have traveled from the hearts of stars to the surface of leaves, from the cold dust of interstellar space to the warm tears on a human face. We have seen how photons, those tiny packets of energy, are captured and transformed by matter in all its forms, by gas and dust, by oceans and atmospheres, by pigments and crystals, by living cells and distant galaxies. We have learned that absorption is not an ending, but a transformation, a way that energy changes form and moves through the universe, shaping everything it touches. The absorption of light is a quiet process, often invisible, yet it is everywhere. It warms the earth, powers life, reveals the composition of distant worlds, and connects us to the stars. Every color we see, every breath of air we take, every thought we think, is touched by the absorption of light in some way. It is a process that unfolds across every scale, from the quantum vibrations of molecules to the expansion of the cosmos, from the flicker of a firefly to the fading glow of the Big Bang. And it is a process that invites us to slow down, to notice, to appreciate the intricate and beautiful ways that light and matter interact. As you rest now, as your breathing slows and your thoughts begin to drift, you can take comfort in knowing that you are part of this vast, interconnected system. The same atoms that absorb light in distant nebulae are present in your body. The same photons that warmed the early Earth are still traveling through space, some of them arriving at your eyes even now, absorbed by the cells of your retina, transformed into the vision that lets you see the world. You are made of stardust, shaped by sunlight, connected to the cosmos by the quiet, constant absorption of light. If you are still awake, know that there are always more stories to explore, more wonders to discover, more gentle facts to ease you into sleep. The universe is vast, patient, and full of mysteries, and there is no rush to understand it all at once. Each night can bring a new journey, a new perspective, a new reason to marvel at the beauty and complexity of the world around us. But for now, let yourself rest. Let the knowledge you have gathered settle gently into your mind, like dust settling onto a quiet plain, like light fading into the warm embrace of matter. You are safe, you are calm, and you are part of something much larger than yourself. The stars will still be there tomorrow, the light will still be traveling, the universe will still be unfolding its secrets, slowly, patiently, without hurry. Close your eyes, if you have not already. Feel the weight of your body, supported and still. Notice your breath, slow and steady, like the rhythm of waves, like the pulse of starlight across the void. There is nothing you need to do, nowhere you need to be. You can simply rest, knowing that the universe is vast and ancient and beautiful, and that you are a part of it. Good night, sleep well, and may your dreams be filled with the gentle glow of absorbed light, transforming darkness into warmth.